Hi everyone, happy Tuesday. MLinguist here. Today's video is going to be about retrieval augmented generation, or RAG for short. To better understand RAG, we first need to understand what a typical generative model process flow looks like. Let's say I had a question about oxygen production, and I input that into a generative model like GPT-4o. The output I'd get would be a decent answer based off the knowledge the model has access to only. However, I want to make sure that the information I'm receiving is accurate and up to date, so I asked ChatGPT to cite its sources. As you can see, it does provide links, but the links are general and unrelated to the subject. This poses the question, how can we make generative models more reliable by reducing their chances of hallucinations, improving the accuracy of their responses, and increasing their use cases through customizability? How do we augment it? Here's where retrieval augmented generation comes in. By giving the model access to specialized information on the subject you're asking about via an information retrieval system, we can augment the accuracy and customizability of the generated content. This is what sets apart RAG models from other generative models. Here's an overview of a typical RAG process flow. Notice how the base process from prompt to answer remains the same. There's just an additional input of documents in a field called context. The cool part about these indexed documents is they can be about anything, which enables anyone, from corporations with detailed documentation to avid world builders with hundreds of imaginary worlds, to create Q&A systems or chatbots on the information they store in the database. We're going to focus on the versatile retriever portion of the model for the rest of the video. So, can we build one? If so, how? Although the process can seem a little long, it's definitely rewarding. We're going to walk through a sample workflow with the following project idea, creating an interactive virtual paleontology encyclopedia. Phase 1 is data preparation. During this phase, we gather a corpus of text data or documents that the retriever will work with. We'd ideally scrape through conference papers and academic research on paleontology from a variety of journals and sources and compile a database of these documents. Next step within the data preparation phase is to pre-process our documents by cleaning, tokenizing, and normalizing the data to prepare it for the next phase. When we clean the data we gathered from the various paleontology journals, we make sure our data is both accurate and relevant, removing any formatting errors, duplicate articles, and more. For this stage, I recommend using the Pandas library, but another library that's good for data cleaning is OpenRefine. In the tokenization step, we break down text into smaller units for the model to process. Some tools I've used in the past for this are Spacy and NLTK, and both are solid Python libraries for this use case. Finally, when we normalize the data, I typically just stick to Pandas, but some alternatives are scikit-learn and auto-normalize. I'll make sure to link all these tools in the pinned comment for easy reference. Moving on to Phase 2, Model Training and Encoding. Phase 2 has two main steps, document encoding and query encoding. These are essential steps to the function of the RAG model we're creating, so let me elaborate with more visuals. First, we encode the documents in the corpus by choosing a suitable model to generate embeddings for each one. I recommend using BERT via the Hugging Face Transformers library or the Sentence Transformer library. But wait, let's briefly go over what embeddings are before we get too far in the weeds of this. Embeddings represent complex, high-dimensional data like words, images, and more as lower-dimensional vectors that capture the semantic meaning and relationships between the data points. This vector representation allows for mathematical operations and comparisons, which makes it easier for models to analyze and process the data. In the case of our model, embeddings make it easier for the retriever to match relevant documents to the user's prompt. Okay, back to the encoding. Document encoding is essential to the process, as it's basically half of the backbone of the retriever, helping the model understand the contextual relevance of the documents in relation to the queries. The other half of the backbone is query encoding. Query encoding transforms incoming queries to the retriever into a format that can be compared against the document embeddings. We can select and apply a model similar to the one used for document encoding, but it's important that our system for query encoding is robust and consistent enough to handle the varied inputs of users to our system. For the purposes of our paleontology example, we'll use BERT for this as well. Moving on to phase 3 of 5. This is arguably one of the most important phases after data preparation because it's essentially the foundation of our retriever. The first step is indexing, which involves building and storing an efficient index of document embeddings. During indexing, documents are collected, parsed, and stored in a way that facilitates fast and accurate retrieval. The index essentially reduces the documents to their informative terms, making it easier to search through large data sets without scanning every document sequentially. Some examples of indexing tools could be Elasticsearch, Apache Solr, and Llama Index. Now on to similarity search. Once the index is built, the next step is similarity search. This involves implementing and optimizing the retrieval mechanism to find and rank the most relevant documents based on the query embeddings we generated previously. On screen are some examples of similarity search algorithms like FACE, Elasticsearch, ChromaDB, BM25, and TF-IDF. We can pick one, say BM25, and configure it to get the top N documents relevant to the query from our corpus. I plan to make more in-depth videos on different similarity search algorithms at some point, so let me know down in the comments if that is something you'd like to see in the future. Phase 4 consists of evaluation and fine-tuning. The right evaluation metrics can give you a better window into how the RAG model performs, and some examples of metrics that can be used to assess the function of the model are the F1 score, mean average precision, and average precision. These evaluation metrics will give you a sense of how good our model is, and we can fine-tune it by tweaking our retrieval parameters or changing our encoding models to improve the results. The final phase is integration and deployment. The main steps in this phase will be connecting the retriever to the generator, deploying the app, and continuing to maintain and update it as time goes on. Since this phase focuses more on the RAG system as a whole as opposed to just the retriever part, I'm not going to cover it as in-depth in this video. Well, there you have it, an overview of retrieval augmented generation for all skill levels. I'd be happy to answer any questions in the comments. Thank you all for watching, and please consider subscribing to stay up to date with future content like this.